Picking up where we left off, we'll define a new kind of echelon form of a matrix called reduced row echelon form. And this will be the one we prefer when we solve systems of equations. It eliminates the need for that back substitution stuff. A matrix is in reduced row echelon form if all its pivots are 1 and all entries above and below the pivots are 0. Okay, so two new things. We're requiring the pivots to be in the usual down and to the right configuration. So it is a row echelon form. We're requiring those pivots to be 1, and we're requiring not only below, but above each pivot, all entries are 0. Okay, so it's a few more steps to take a matrix from row echelon form to reduced row echelon form. Our little protocol has been to use a pivot, and we preferred one in the past, but didn't demand it. Use that pivot to eliminate all of the entries below that pivot, to make all the entries below that pivot 0. Well, we'll just add a few extra steps to make all the entries below and above that pivot equal to 0 with similar types of manipulations. The little protocol we've set up, we'll follow it in the same order and we'll be fine. Just adding extra steps of eliminating entries above pivots, and when all's said and done, making sure the pivots are in fact 1. Probably trying to avoid fractions as well along the way. Okay, so let's look at page 68, number 2. 68, number 2. Here we go. Okay. Put this matrix in reduced row echelon form. Okay. This actually, we encountered this matrix in number 2A above in the previous video, where we had put it in row echelon form in this sense. So see the previous examples for the row operations where we reduce this down to this particular form. I think we probably gave two solutions, one where we didn't have the pivots being 1, and then we did a couple of extra steps and made the pivots 1. So we have a row equivalence here, but this ain't reduced row echelon form because above this pivot is a 3 and above this pivot is a 1. Got a 0 up here. So that entry currently appears good. We'll see what happens in the remainder of the process. Okay, so let's start with a matrix. We'll follow the steps as given above. So that's already done. Let me borrow that. And now we want to get, say, let's look at the second column. Let's get a 0 there. We'll use this 1 to get a 0 there. All right, so the strategy will be take row 1 and subtract 3 times row 2 so that we get 3 minus 3 times 1. Sure enough, that'll get us the 0 entry there. Oh, by already having zeros, I guess right here, by having a 0 here, that won't change anything above or below, as we've done some of the steps already. So we keep the 1 here, the first column stays the same. We've got a 0 up here. That 0 I was happy to have here. Well, it's gone now, but we had to do it in this order. And what we're doing, it's the same thing we did in row echelon form, except making things both below and above pivots equal to 0. So you want to think, fix the first column, fix the second column, fix the third column, and so forth. We had been fixing things in terms of first and second and third and so forth columns when we did row echelon form. Well, same thing, but now fixed requires zeros both above and below the pivots. You don't want to make these pivots 1 just yet. That's okay. If the arithmetic is easier and helps you avoid fractions, I'm fine with that. In the end, we'll have to make sure we get pivots of 1. So when I say fix a column, I mean pivot with 0 entries below it. Pivot with 0 entries above and below it. Pivot with 0 entries above and below it. So we ain't done. We need to use this 1 to eliminate that 1 and that negative 3. So we'll add 3 times row 3 to row 1, add 3 times row 3 to row 1, and we'll subtract row 3 from row 2 minus row 3. And that'll produce, in fact, that produces an identity matrix. This is in reduced row echelon form. All the pivots are 1. There's zeros above and below the pivots. It could be we have pivot-free columns. I'm not saying in a reduced row echelon form that will always have nothing but zeros and ones. It depends on the matrix. If it's a matrix with a pivot in every column, then yeah, we'll only have entries of zeros and ones in that case, in the reduced row echelon form. And there's an extra little comment here. Gee, when we did the row echelon form, there was an infinite number of row echelon forms for a given matrix. Well, with the reduced row echelon form, guarantees there's a unique reduced row echelon form of a matrix. Let's abbreviate that REF. REF we had mentioned in passing. These are common commands in software to put matrices in row echelon form, or RREF, reduced row echelon form. But unique version of a reduced row echelon form. So there's only one answer if you're asked, take this matrix and put it in reduced row echelon form. Let's look at one involving systems of equations. All right, so here's a system of equations. The instructions come to us as, put the augmented matrix in reduced row echelon form and solve it. This is number 16b. Let's speculate. 16a dealt with back substitution. Yes, we've already done this one. Number 16a, we took the augmented matrix, okay, create the augmented matrix for the system of equations. We had put that augmented matrix in row echelon form, pivot down into the right, pivot down into the right, pivot, nothing else. All right, well, let's go beyond that and let's borrow the work that's already been done. So we'll borrow from upstairs the fact that we have row equivalence between this augmented matrix, the one for the given system of equations, and this augmented matrix. We could turn this back into a system of equations and see that z equals 0, substitute that in and find out what y is, substitute y and z into the first equation and see what we get for those. That's how we did it with back substitution. That in itself is a bit of arithmetic. I think elementary row operations are easier. So they're very straightforward arithmetic and oftentimes involve zeros. We make them involve zeros. So let's pick up where we left off with this augmented matrix and just go a little bit further, making all pivots 1 and making now the entries above those pivots 0 as well. Okay, so let's see. First, let's take row 2 and divide it by -2. Let's make this pivot 1 because that doesn't introduce fractions. If it did, I might look for some alternative routes, but this is certainly a correct route and it doesn't introduce fractions, so we're good. Divide the second row by -2 and that produces this second row. Let's use that 1 to eliminate that 1. We want zeros above and below this pivot. So we'll take row 1 and subtract row 2. Notice the 0 doesn't mess up anything over here. That's because we're doing it in a particular order, designed not to mess up things. Do the subtraction, that produces this. And I want to say we fixed the first row and the second row. That pivot, we'll have to change that to a 1 by dividing potentially by 2 at some point. I don't want to do it now because that'd introduce a 1/2 here. But this row, this column is in excellent shape, though I'm not entirely done with it. This column is in excellent shape. I am done with it. It's got all zeros and ones. Over and down, we got a pivot. Let's use that 1 to eliminate this and this, the entries above that pivot. Okay. Got zeros over here. That won't change anything, so it won't mess up the first or second columns because they're already in good shape. By the way, there's a 0 over here, coincidence. That won't change either of these values either. In general, don't bet on that kind of behavior though. So we'll subtract row 3 from row 1 to get 1 minus 1, get a 0 there and all the other stuff that goes on. Take row 2 and add 4 times row 3, add 4 times this entry, that'll give us a 0 there and all the other stuff that happens produces As I said in this section, I'll show all the arithmetic and the examples. Later on, we might streamline it a little bit more. Simplifying, that produces this matrix. This is reduced row echelon form. Not because of that, no. All right, then now the only thing left to do is divide by 2 on this entry. The first column is almost there. Second column's good. Third column's good. End of conversation. We ran out of pivots, so I run out of talking about fixing columns. The augmented column is really not relevant in some sense in terms of this row echelon form and reduced row echelon form. It's the coefficient matrix we want to reduce. We'll state this in a theorem shortly. Okay, so we'll take that first row and divide it by 2. Doesn't introduce fractions. Excellent. And then here's a reduced row echelon form of the coefficient matrix. Now, if we wanted to look at the associated system of equations, we'd get the equation, the variables in this case were x, y, and z. We get 1x plus 0y plus 0z equals -1. We get x equals -1. Here we get 0x plus 1y plus 0z equals 2, y equals 2, z equals 0. You can just read off the values of the first, second, third, and so forth variable by reading off these entries in the final column, provided you've got the matrix in reduced row echelon form. And every column contains a pivot. More details on that shortly. All right. The theorem that justifies us saying that these are the solutions is theorem 1.16. Said, hey, the augmented matrix we started with is row equivalent to this one. So the solution to the system of equations associated with this is the same as a solution to the system of equations we started with. This has solution. X is -1, y is 2, z is 0. So that's a solution to the original system of equations as well. A little educational observation here. We had to do a little bit more stuff, a few more row operations to get this in reduced row echelon form, but we've avoided the back substitution stuff by performing just more elementary row operations. We're going to do so many elementary row operations that's a relatively easy manipulation. So when dealing with systems of equations, the plan will be reduce row echelon form and read off the solution if there is a solution. Oh yeah, and there can be multiple solutions. We've seen examples of that already. Back to the notes. This technique, back to the notes. This technique is called the Gauss-Jordan method, where you take a matrix and put it in reduced row echelon form. All right. Now, this theorem, we'll go through an argument for it, basically says you use the Gauss-Jordan method. It tells you when there's a unique answer, tells you what that answer is, as we just saw in the previous example. It tells you when there's not an answer. There's a way to recognize that. We've seen examples of that. And if there's multiple solutions, it tells you what those are. So, in other words, the Gauss-Jordan method is robust. It gives you what the answer is, what the type of the answer is, whether there's no solution, a unique solution, or multiple solutions. That's the 3 possible outcomes. The Gauss-Jordan method, it takes care of all 3 of those. All right, so I don't get stuck somewhere and get some indecision about the nature of the solutions. We get a totally thorough answer about the nature of the solutions of a system of equations of the form AX equals B using the Gauss-Jordan method. We just got to go through, do the row reduction, and interpret the result. So the theorem says, let AX equals B be a linear system of equations, and take the augmented matrix, A augmented with B, suppose that's row equivalent to H augmented with C, where H is in row echelon form. All right, well, if it's in reduced row echelon form, that's a row echelon form. They've stated it like this to give weaker hypotheses. We'll go for a reduced row echelon form, and this covers that as well. So take the augmented matrix, row reduce it, row echelon form. Claim is the system AX is inconsistent if and only if the augmented matrix, H augmented with C, has a row with all entries equal to 0 to the left of the partition and a non-zero entry to the right of the partition. 2 or 3 examples back, we saw an example of that. What we get out of this row with zeros to the left of the partition and non-zero to the right is corresponding an equation of the form 0 equals 1, for example. Well, 0 doesn't equal 1. I don't care what you choose for the values of this x vector. So that's what they're getting at there. So actually, this is going to be your favorite kind of work. These that have no solutions, these that are inconsistent, because as soon as you see this kind of behavior, zeros to the left of the partition and a non-zero entry to the right, you're done. You don't have to go further to get things in reduced row echelon form and all that. You know there's no solution once you see that kind of behavior. So these are the quickest kind of work, it turns out. AX equals B, the system of linear equations, is consistent, and every column of H contains a pivot. Then the system has a unique solution. So if consistent, every column has a pivot, then unique solution. By the way, you can easily read that unique solution off like we did in the previous example. So they've broken it into inconsistent, consistent with a unique solution, and this last one will be consistent with infinitely many solutions. If AX equals B is consistent and some column of H has no pivot, so we'll have a pivot-free column, as we'll call it, the system has infinitely many solutions with as many free variables as there are pivot-free columns of matrix H, the row-reduced version. Okay, so what's going on here, we'll elaborate on when we work more and more examples. We've only seen one free variable in a system of equations so far, but there could be more than one free variables. I guess there's one for every pivot-free column. I mean, that's the claim here. And none of this will be surprising to you once you get experience working a bunch of these examples. Let's go through proof of that. Okay. Taking big advantage of theorem 16, theorem 1.16 or 1.6 was it? That I know if these are row equivalent, the solution to the systems of equations associated with H augmented with C is the same as a solution A augmented with B. All right, so claim is, let's go through the first part. System is inconsistent if and only if H augmented with C has a row with all entries equal to 0 to the left of the partition and a non-zero entry to the right of the partition. Something of the form 0 equals not 0. So you got a problem with that. Okay. If H augmented with C has a row, say row I, of all entries of 0 to the left of the partition and a non-zero entry, call it C sub I, not 0, to the right of the partition, then this row corresponds to the equation 0x1 plus 0x2 up to 0 times x sub n equals C sub I. In the system of equations, hx equals C. Taking the augmented matrix, turning it into a system of equations, the ith of those equations corresponding to row I of the augmented matrix, the bad row that has a bunch of zeros and then a non-zero entry. So we get that correspondence. Theorem 1.6 says the solutions to AX equals B and HX equals C are the same. That's why we do this row reduction stuff. Of course, the plan is to make this a system of equations. It's easier to solve. Well, there's no solution, x1 through x sub n, that's going to make 0 times x1, blah, 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 plus 0 times x sub n equal to something that ain't 0. This is 0. If that's not, no solution. So hx equals C, that system of equations has no solution. Solution set is empty, so it's stated here. So AX equals B, that has no solution. The solution set is empty. In other words, the original system of equations is inconsistent. That was only half of the story for part one. That was if we had that row of zeros, then we had no solution. We still need to consider the converse of that, and we will around the end of this. All right, second claim was about unique solutions. Ready for the second claim? Oh, not yet. So here we're doing a piece of the converse already. Now suppose H augmented with C has no row with all zeros to the left of the partition and a non-zero entry to the right. We'll show that AX equals C has a solution and it's consistent. This is the part we'll produce later. If a row is all zeros on both sides, so I still owe you some stuff. This is the thing we'll do at the end. All zeros on both sides of the partition corresponds to an equation of the form really 0 equals 0. That means that don't mean anything. That's no information. That's satisfied for any values x1 through x sub n, contributes no new information. We could really eliminate that row, symbolically define H prime and C prime by eliminating the rows of zeros in HC. And then we'd consider the new augmented matrix H prime, C prime. In that case, every row of H prime would contain a pivot because we've eliminated all those rows of zeros underneath. And now if we've got pivots, we're in business. So here's where we'll shift to part two. If every column of H prime, and so every column of H contains a pivot, then each x sub j is uniquely determined and the system's consistent. Just like we did in the previous example. You'll go through and take that first row, first column, that very first entry. That'll be the coefficient of x. You can solve for x in terms of the other stuff. Second row, second column, got a pivot. You can solve for x sub 2, say, in terms of the other variables. On down to the final row allows you to solve for the final variable. It's the back substitution because these guys have put things in row echelon form versus reduced row echelon form. But you can use back substitution if there's pivots in every column to find all of the x sub j's, and they are uniquely determined. If the system is consistent and we have a column without a pivot, then x sub j can take on any value. Like in the example we did earlier, it plays the role of a free variable. So what it amounts to is we can solve for the other x's that which are in columns that correspond to variables containing pivots. The pivot containing columns will allow us to determine if the ith column contains a pivot, allow us to determine x sub I in terms of the other variables, which are acting as free variables. So if we have a pivot-free column, and really the example illustrates the idea, better job than I'm doing. If we have a pivot-free column, whatever variable corresponds to that column, that's going to give us a free variable. That variable will act as a free variable. So if we've got a consistent system and we've got pivot-free columns, these pivot-free columns are contributing free variables. We're getting infinitely many solutions, not that everything is a solution. The solutions come in particular forms, which we can read straight off of the final augmented matrix, preferably the reduced row echelon form of the augmented matrix. Let's see. We're getting unique solutions. Condition 2 yielded unique solutions. This is where we had a consistent system with pivots in every column. And you just read those off using back substitution, or better yet, put it in reduced row echelon form and then read those off. In condition 3, we had a consistent system, but we had pivot-free columns. Well, those are contributing free variables, and so those are contributing multiple solutions. All right, so If consistent, then we had this kind of behavior. If inconsistent, we were able to recognize it, and we see from this other stuff, the only time we'll get inconsistent is when you get something of the form 0 equals 1 or 0 equals non-zero in the reduced row echelon form, say. So Gauss-Jordan method gives you answers unambiguously. We'll do some more examples at the end and do some applications that require solutions to systems of equations. First, a little bit on matrix multiplication. A matrix that can be obtained from an identity matrix by means of one elementary row operation is an elementary matrix. So you start with an identity, you do one thing to it, that resulting matrix, one elementary row operation, that resulting matrix is called an elementary matrix. So if you took the identity matrix, swap 2 rows, that's an elementary matrix. If you took the identity matrix, multiplied a row by 3, that's a new elementary matrix. If you took an identity matrix and added 3 times the first row to the third row, that's an elementary matrix. One elementary row operation as applied to the identity matrix creates a thing called an elementary matrix. Now, why you want to be interested in these? Well, they're intimately related to elementary row operations. Theorem 1.8 says, let A be an m by n matrix and E an m by m elementary matrix. Multiplication of A on the left by this elementary matrix affects the same elementary row operation on A that was performed on the identity matrix to obtain matrix B, matrix E. So the row operation that you did up here is done to matrix A by multiplying matrix A on the left by the corresponding elementary matrix. So if you created matrix E by swapping the first 2 rows of an identity matrix, take matrix E of the appropriate dimensions, multiply matrix A on the left by that elementary matrix, and what you'll get is the swapping of the first 2 rows of matrix A. You'll get a new matrix. It differs from the original matrix by that elementary row operation. All right, let's go through proof. The homework covers all 3 types of elementary row operations. Is what? Row interchange, row addition, and multiplying by a scalar. Exercises 52, 53, and 54 cover those. Let's go through the first one. The second one's quite similar. And let's show that row interchange, creating an elementary matrix by row interchange, allows us to perform that same row interchange on a matrix A of appropriate dimensions. All right, so suppose elementary matrix E results from interchanging row I and row J of an identity matrix of appropriate size. I think it was m by m with the parameters they had. I'll just blanketly state appropriate size. We didn't necessarily have square matrices when we were looking at matrix A, but we did for the elementary matrix. Elementary matrices are square matrices because they're modified identity matrices, and identity matrices are square matrices. So suppose you take identity matrix I, interchange rows I and J to create elementary matrix E. All right, this is going to require us to delve into the definition of matrix multiplication. Now, it's a bunch of symbols. It's nothing more than the definition of matrix multiplication, you know, row times column in a dot product sense. The bulk of this is going to be straightforward because this matrix E, well, a bulk of it's an identity matrix. The only place where matrix E is not an identity matrix is in row sub I and row sub J. And even there, you got a bunch of zeros. All right, so what does the entries in matrix E look like? Well, the kth row of matrix E is a vector of all zeros with a 1 in one spot, all but 1 zeros with a 1 in one entry. Now, if we're looking at the kth row where k is not I or j, that is, it's not one of the rows that have been interchanged, then the non-zero entry, the 1, occurs in the kth component of this row of matrix E. So the kth row vector would have a 1 in the kth entry, except in those rows where we've done the interchange. When we've done the interchange, when k equals I, the non-zero entry is in the jth entry, not the ith entry, because we've done the swap. For k equals j, the non-zero entry, the 1, is in the ith entry, not the jth entry, because we've done the swap. So the 1 appears in the kth row, in the kth component, the kth entry of this row vector, except in the ith row. And in the ith row, the 1 appears in the jth entry, and in the jth row, the 1 appears in the ith entry, because we've swapped row I and row j. All right. So let matrix A have entries A sub ij, let matrix E have entries E sub ij, and we spelled out specifically what those are. And to have it have a name, we're going to multiply A on the left by E, and we should get out a matrix that's the same as A, except the ith and j rows have been interchanged. That's the claim. All right, call the entries B sub ij, the entries of this product, just to give them a name. Let's see what the kth row of B is. All right, think what's going on. Kth row of B, that ought to be, most of the time, the same as the kth row of matrix A. In general, kth row, here it is given in terms of the double subscripts, and here's how you compute those using the definition of the product of matrices. B sub KL would be a product, sum from P equals 1 to N of the product, E sub KP, A sub PL. P is a dummy variable. We're doing a dot product here. We're running along these entries as P varies, runs along the kth row of E. And these entries here run along the lth column of A, the second matrix. Yeah, and we're looking for the KL entry. That's definition of matrix products. Take a peek back at the definition. It's straight up definition of how you multiply matrices. I understand it gets a little garbled with all the letters and stuff. Now, if K isn't I or J and you didn't do the swapping, then piece of cake. What do you get for the E sub KPs? All of them are 0 except the kth one. When P equals K, we'll get 1. All the others are going to be zeros. So when you do the sum running across that kth row, and it looks something like this, you get 0, 0, 0, 0, 0. You run across a 1 at one point, at the kth point, and followed by a bunch of zeros. So when you do this summation stuff, all of these are going to be 0 except when P equals K. And we get E sub KK. Remember, this E matrix looks a lot like an identity matrix, except in 2 rows. E sub KK, that'll be a 1. The only place we don't get a 0, we get a 1 in that row. All right, this occurred when P equals K. If P equals K, we get E sub KK here. We know it'll be a 1. P equals K, that'll give out A sub KL here. And remember, this is the KL entry of matrix B from the definition up here. All right, 1 times A sub KL is A sub KL. Hey kids, look at this. B sub KL equals A sub KL. We're looking at the kth row of matrix B. L ranges over, I think it's 1 to M. Is that right? Depends on the dimensions of matrix A. Like I said, it runs over its values. But we're looking at a fixed K. L is valid over its range. And we're getting that the entries in the kth row of matrix B are the same as the entries in the kth row of matrix A. Kth row of matrix B, same as the kth row of matrix A. Yeah, that's the rows you didn't change. So they were supposed to be the same. Now what's going to happen is we're going to look what happens when we take K equals to I. What you're going to get is the jth row of matrix A. in matrix B. And when k equals j. When k equals j, you're going to get the ith row of matrix A in matrix B because of the interchange. So let's take a look at that. This is the formula we'll take with us. Formula valid to determine entries in a matrix product. All right, so take k to be something other than, take k to be I and j, that's what's left. When k is something other than I and j, we had the kth row of B and the kth row of A is the same. I verbally said that last page. Moving on to k equals I and later to k equals j. Let's see what happens. When k equals I, okay, all those E sub k p's are 0 except for one of them. The one that isn't 0 occurs when that second index is j. E sub k j is the non-zero one. Hey, we're looking at k equals I. You would expect it to be E sub ki, the ith one. But remember, we swapped the ith row with the jth row. So when k equals I, E sub kp is 0 except when p equals j. Down here, we'll interchange the rows of I and j. Yeah, because we've interchanged the rows, the ith row and the jth row of matrix A. So we get B sub KL from the formula above. We're taking K to equal I, so if you like, that's B sub IL. Same story, a bunch of zeros. The only time we don't get zeros when P equals J. Okay, P equals 1, say we get zeros. P equals 2, we get zeros. We get a bunch of zeros. P equals J, we'll get E sub KJ, A sub JL, and then a bunch more zeros. E sub KJ, A sub JL. E sub KJ, that's 1. The only one we get in that particular row. We're doing a row times column thing. There's the one that we get out. And that produces an A sub JL. We've got B sub IL equals A sub JL. L ranges over whatever appropriate values. Okay, then this is the entries in the ith row of B, and this is the entries in the jth row of A. Right, the ith row of B equals the jth row of A. And guess what? Do the same thing with k equals j, same kind of formula, but with the i's and j's interchanged. The jth row of B equals the ith row of A. Right, matrix B has as its jth row the ith row of A, has as its ith row the jth row of A, ith row of B, jth row of A, jth row of B, ith row of A. So it's got this little flipping in here. Indeed, matrix B, the elementary matrix times matrix A, satisfies the condition that it's the matrix that has interchanged row I and row J of matrix A. That elementary matrix has done this elementary row operation. Same thing holds for row addition. Here's the proof. Knock yourself out. It's tedious, but it's really just arithmetic. And the same holds as well for multiplying a row by a scalar. So there's row interchange. There's actually the solution to number 52 is the exercises. The one I didn't go through was number 54. Number 53 is the row scaling elementary row operation. You do 3 things with elementary row operations: row interchange, row addition, and row scaling. So each of those can be represented by elementary matrices. All right, let's actually illustrate some of that. Consider this elementary matrix. Where did it come from? Well, that's a 3x3 identity matrix where we swap the first 2 rows. So if we took a matrix A and multiplied it on the left by this matrix, it had swapped the first and second rows of matrix A. So let's illustrate that. So this, here comes a less theoretical, more computational, and easier to see stuff. All right, so take matrix A, multiply it on the left by this thing. This is an elementary matrix that differs from the 3x3 identity matrix by having had the first and second rows interchanged. You do this product, let's multiply by matrix, say 1, 2, 3, 4, 5, 7, 8, 9. I can distinguish between the entries by making them all different. We'll do our row times column thing. We'll think what happens. First row, first column, that's going to pick off the 4 because of the zeros. First row, second column will pick off the 5. First row, third column will pick off the 6. So we'll get 4, 5, 6 in the first row of the product. Similarly, the 1 will pick off the 1, the 2, and the 3. I mean, here's all the arithmetic. And then when we do the third row times each of the columns, we get behavior like an identity matrix. And indeed, it interchanged the first and second rows. Elementary matrices, this is the reason we're doing elementary matrices. Elementary matrices can be used to perform elementary row operations, provided you multiply on the left. Not our problem. If you multiply on the right, it won't interchange the first 2 rows. It'll do something involving column interchange. Some people live perfectly happy lives doing not only elementary row operations, but also elementary column operations. That's not our problem. But you're multiplying on the left and getting row operations. If you multiply it on the right, you'll get column operations. I think there's an example buried somewhere in the exercises that brings up column operations. Okay. So if A and B are row equivalent, then there's some matrix C that will, when multiplied on A on the left, will produce matrix B. That matrix C, in fact, is a product of elementary matrices. How did you turn A into B? With a sequence of elementary row operations. Okay, well, each of those elementary row operations can be represented in order by an elementary matrix. Multiply all those elementary matrices together in the appropriate order, take the product of those elementary matrices, and that'll tell you what matrix C is. All right, so let's go through some more numerical stuff, and then we'll call it a day. All right, so here, they say, find a matrix C such that when we multiply C by this matrix, it produces this matrix here. Okay, now this isn't related to the elementary matrix stuff. This is just related to the systems of equations stuff. End of the chapter, we'll just illustrate 2 or 3 things. We'll do some elementary matrix stuff again shortly. Okay, well, how big would that matrix C have to be? Let's see, it'd have to have 3 columns. So we could do the row times column thing. If they have 3 entries side to side, the number of columns would have to be 3 in order for the product to exist. So it would have to be something by 3, because this is 3 by 2. The result is also 3 by 2. So the other dimension of matrix C would have to be 3 as well. C needs to be a 3 by 3 matrix. If I take a 3 by 3 matrix, multiply it by a 3 by 2 matrix, this 3 is the same as the 3 and 3 by 2. That would yield a 3 by 2. First dimension of C, second dimension of this thing will be the dimension of the product. So C has to be 3 by 3. This 3 for the product to exist, and this 3 so that the product has 3 rows. How many columns will the product have? Well, how many products does the second matrix have? Or how many columns does the second matrix have? 2 columns in the product. So to get a 3 by 2 out, we'll have to take C to be a 3 by 3 matrix. Okay, well then let that be its entries. So symbolically, just take these letters and go to town. All right, so if we're going to take this matrix, C times a given matrix, we want it to equal this, then we get the following. Do your row times column thing. Okay, it's a little messy, but it produces all of this stuff here. As I said, I'll put all the details in, the computations in the notes initially. We'll streamline it here soon enough. Okay, so that produces this bunch of equations. So we need this to be 1. We need this to be 2, and so forth. That gives us, we got 6 entries. That gives us 6 equations. Yeah, gives us these 6 equations. So I needed the first row, first entry on the left to equal the first row, first entry on the right, and so forth. All right, so this is the requirement from those system of equations to have the entries in the matrix on the left to equal the entries of the matrix on the right. Makes me breathless. Okay, how we doing? C11, C11, C12, C12, C13. This is 2 equations and 3 unknowns. All right, so here comes the system of equations stuff. So are these other 2. So notice the first subscripts are 1s in these. The first subscripts are 2 in these 2, and the first subscripts are 3 in these 2. So we've actually got 2 equations and 3 unknowns 3 times over. Okay, I know how to solve those. Let's make augmented matrices. Okay, so for each of these systems of equations, we have the corresponding augmented matrices. So let's one by one go through and put them in reduced row echelon form, because that's a big topic in this section, and find solutions. How many solutions are you going to get? Is it a unique solution? We need a pivot in every column left of the augmentation to get a unique solution. Are there 3 pivots? Well, there ain't room for 3 pivots. There's only room for at most 2 pivots in each of these, because there's only 2 rows. So we're going to have a pivot-free column. That means what? Free variable. We're going to have a free variable in each of these as well. Okay, that means infinitely many solutions, which is good. We're just looking for 1. So they're out there. Okay, so let's put this first one in reduced row echelon form. Let's practice that a little bit more. It says let's take the second row and divide it by 2. Okay. Dividing through by 2, it lowers the numbers. If you don't want to do that, don't do that. Let's use this 1 to eliminate that 1. Okay, so we'll take row 2, goes to row 2 minus row 1. And that produces this. Let's make this 1 now. Let's multiply the second row by 1. Oh, first column, we're done with the first column. You'll never touch the first column stuff again. We're trying to fix the second column. I want a 1 there. I got 2 ideas. I could use this -1 to eliminate that 3 and later change that to a 1, or change it to a 1 now by multiplying the second row by a negative. Okay, that gets the 1 there. And now using the 1 to eliminate the 3. So the order in which I do this is arguable. But do those manipulations. Now you've fixed the second row. First row's good, second row's good. You've run out our column. First and second columns are good. Nothing you can do with the third column without messing up the first 2 columns. So you're stuck with this pivot-free column. Let's call that augmented matrix 1. Okay, so from this we can find solutions to this system of 2 equations and 3 unknowns. Okay, so now we got to do that 2 more times. I've numbered them so we can come back and look at what we have from above. Let's take that second system of equations. Row echelon form, similar manipulations. I leave it to you to read these in detail. You've got the video that you can pause. You've got the notes posted online. So let's not spend all our time on the arithmetic. Ditto. Okay, so we'll take the second and the third and reduce those down, and notice as predicted, hey, look at that pivot-free column. Nothing I can do about that pivot-free column. Same thing down here. I see some similar numbers even. Anyhow, we've got 3 systems of equations in 3 unknowns. We've taken them down to reduced row echelon form in terms of the augmented matrices. Let's take number 1 from the previous slide, number 2 and number 3, and let's rewrite those as systems of equations. Okay, that first augmented matrix, rewriting it, we had 2 equations and 3 unknowns. We'll produce this. Let's, as we've done, solve for first unknown, second unknown, third unknown. Problem is you don't have any information. You only have 3 pieces of information. You know there's going to be a free variable by theorem 1.7. Move this stuff to the other side. C11 must be 1 plus 5C13. C12 must be 0 minus 3C13. What about C13? Well, I don't have any information about C13. That'll be the free variable. Why is that? Because much like these, it was the third column that was pivot free. So it's the third unknown that will act as a free variable. And that'll happen these 2 times as well. So similar process, turn this back into a system of equations and do the same type manipulations. And then finally this one. So we've got a, let's see, it's a -5 and a 3 and a -3 and a 1. -5 and a 3 and -3 and a 1. Yeah. So take the second augmented matrix, turn it back into a system of equations. Solve for C1, C2, C3. We get something of this form. Do the same thing for the third system of equations. Now, if they wanted a general solution, I'd introduce free variables and write it in terms of those free variables. Doing something a little bit different. We just want a matrix C, and these are the entries. Okay. So in terms of the C1, 3, C2, 3, C3, 3, it was preferentially the third one. The Gauss-Jordan method is going to make the free variables the ones that are kind of further to the right. Because of the down and to the right thing, it's going to push free variables to the right, and they'll preferentially be the ones with higher indices. I ain't saying they'll be the highest indexed ones all the time, but in some sense, they're preferentially higher indexed. So anyhow, these could be anything. Your favorite number, I hope, is 0. So let's let them be 0. That'll make the arithmetic easy. Okay, and then I go back and substitute. I don't have the C11 in front of me. I got the C21 in front of me. If we choose C13, C23, C33 to be 0, here, for example, we'll get C21 is -3, C22 is 1, and I said make C23 0, so you lose this. So we get a -3 and a 1 for C21 and C22. Down here, we'll get -9, 3, and 0, -9, 3, and here's the 0. And similarly for the first one from the previous slide. So we have found values of for all 9 of those unknowns, C11 through C33, that satisfy those systems of equations. So they do the desired thing. There's one matrix C that we could use that would give us the desired product. You got another one? Yeah, you could have let each of these things be 1, or you could let this one be 1 and these two be 0. So I got an infinite number of ways to choose these Cij parameters. This is the easiest way, probably. I'm taking those free variables and setting them equal to 0. All right, something else with more explicitly elementary matrices. They don't state it exactly in terms of elementary matrices, but there's a big hint right there. It says, let A be a 4x4 matrix. Find a matrix C such that the result of applying the sequence of elementary row operations as given to A can also be found by computing the product C times A. Okay, notice they're multiplying A on the left by matrix C. So the plan is we want C to do the following. In order, first interchange row 1 and row 4. Well, I could find an elementary matrix that does that. Next, add 6 times row 2 to row 1. Well, I could find an elementary matrix that does that too. Add -3 times row 1 to row 3. Add -2 times row 4 to row 2. These are all elementary operations. So can be represented by a first, a second, a third, and a fourth in order. Order's going to matter. Elementary matrix. So that's the plan. Find elementary matrices. We need one that interchanges row 1 and row 4. We're talking about a 4x4 matrix. We'll take a 4x4 identity matrix then. You want to interchange row 1 and row 4. Do that to the identity matrix. This is an elementary matrix. Let's call it E sub 1. We need to find 3 more. Secondly, add 6 times row 2 to row 1. Add 6 times row 2 to row 1. Thirdly, subtract 3 times row 1 from row 3. Fourthly was subtract twice row 4 from row 2. So here's the elementary row operations they wanted. Here's the corresponding elementary matrices. Let's take a look at each of these are scalar additions, adding scalar multiples of rows. So let's look at those. We haven't seen one of those just yet explicitly. We want to take row 1 and add 6 times row 2. You took the identity matrix, so we'll multiply by 6 and add. That'll just pick up a 6 right there. Picks up a 6 right there. Here we've subtracted 3 times row 1. Done that to row 3. Subtracted 2 times row 4. Row 4, be that fourth entry. You've done that to row 2. It happened in the second row. So what you've got when you do this row addition stuff is you pick up the coefficient of that row that you're adding or subtracting. You pick those up in specific locations, depending on which row you're subtracting and which row you're subtracting from, for example. All right, so we get E2, E3, E4 are the elementary matrices that represent these elementary row operations. All right, we want to do all that stuff in order. Okay, to do all that stuff in order, let's take matrix C to be E1 times E2 times E3 times E4. We're going to write them down. This is a little odd. From right to left instead of left to right. Why is that? Because we're going to multiply on the left A by this matrix C. So if you imagine an A being written right here, first thing we want to do is what E sub 1 does. Do that to A. Secondly, what E sub 2 does. Thirdly and fourthly. So we've written them in this order because we're going to multiply A on the left by this. So I want E1 reaching A first. You write them in the opposite order, E4 will reach A first, multiplying on the left. And you don't multiply on the right, not in here. Okay, so we'll take C to be the product of those in this particular order. Won't bore you with the arithmetic, but we'll do our row times column thing for the first two. That'll produce this. Second two, that'll produce that. You can go through all the arithmetic or, think what would happen. What you're going to do to this matrix here, what was this? 6 times row 2 added to row 1. We could think of that elementary row operation being performed on this matrix as well. I don't want to get into the arithmetic. But do the matrix product or whatever, and it'll produce this matrix here. So here's what we get for a matrix that would do all of that stuff. You can represent an elementary row operation by an elementary matrix multiplied on the left. You can represent a sequence of elementary row operations by a product in the appropriate order of elementary matrices. This will play a big role in the next section when we talk about inverse matrices and why the technique that we're doing works. And finally, something that's from a little different setting but leads us to systems of equations. We're totally set up for systems of equations now. Question is, find A, B, and C such that the parabola y equals ax squared plus bx plus c passes through these 3 points. How you know they're points? Parentheses. If they were vectors, I wouldn't talk about them in this setting and I'd use different notation. Okay, so they want this parabola with A, B, and C as its parameters or whatever to pass through these points, x and y. Okay, so we'll plug the x and y into the formula 3 times. Plug -4 in for y, plug 1 in for x, produces this. Plug 0 in for y, -1 in for x, produces this. 3 and 2 respectively produces this. Take these equations and let's write them in a little cleaner way. So this first one gives us a plus b plus c equals -4. There's the first equation. Second one gives us a minus b plus c equals 0. A minus b plus c equals 0. And the last one gives us a 4a plus 2b plus c equals 3. Right. Hey, that's 3 equations and 3 unknowns. You think it's got a unique solution? I hope it's got a unique solution. If not, they've asked us a bad question. If it happened that these points were collinear, something would go wrong. We'd find out about it. What would happen is we'd probably have to get the a to be 0 out of this, and we really don't have a parabola. We've really got a straight line. I'm trusting that they haven't given us a bad problem like that. So this should have a unique solution given the nature that they've asked the question. Okay, take the system of equations, coefficients, 114, 114, and so forth. Augmented with -403, -403, taking the only information they gave us, writing it in terms of stuff we know. Let's row reduce. Okay, let's use this one. Let's put it in reduced row echelon form. So let's go through this one in a little bit of detail. Use this one to eliminate this 1 and 4. We'll subtract row 1 from row 2, subtract 4 times row 1 from row 4. There's the elementary row operations. It's not write all that down just anymore. And here's the arithmetic. You need to be a little bit careful when doing this because it's easy to mess up an entry. Then we'll check the answer when we get done if necessary. But here's the row operations, and these are correct because I have gone through these numerous times checking arithmetic. And we got the first column the way we want it. Okay, how about the second column? I want a 1 there. You want to divide by -2? Let's do it, because it won't introduce fractions. So let's divide the second row by -2. All right, so that gets us a 1 for the pivot there. By the way, is this a row echelon form? No, pivot down to the right, pivot straight down, pivot. It's not row echelon form, so there's work to do. Let's use this 1, if we were going for row echelon form, to eliminate this -2, but we're going for reduced row echelon form, and use this 1 to eliminate that 1. I want zeros above and below the 1 in reduced row echelon form. Okay, it's the first one of those we've done from scratch. So do both of those. Take row 1, subtract row 2. Got to get a 0 there. Won't mess up anything in the first column. We're done with the first column. Take row 3, add twice row 2. Gets a 0 there. Doesn't mess up anything over there. We're done with the first column, I said. So you do the arithmetic. It produces this. You like the looks of this? Yeah, first column is totally good to go. Second column, totally good to go. Third column needs some work. I want a 1 there. You want to divide by -3? I guess so. It won't introduce fractions. So let's divide the third row by -3. Gives us a 1, and I think we had a 15 there. Divided by -3 produces a -5. All right, good, pretty good. Need to get rid of that 1. Let's use this third row. Subtract it from the first row. That'll get rid of the 1 that was there, and some other things happen. Some other things happen arithmetically, giving us a coefficient matrix that is in reduced row echelon form. Any pivot-free columns in the coefficient matrix? Nope. This column's pivot-free, but we had this conversation about the coefficient matrix. H is what we called it in the theorems upstairs. Right, each column of the coefficient matrix has a pivot, so unique solution. Consistent system. So we'll take the first unknown to be 3. The letters we use were A, B, and C. So A equals 3, B equals -2, C equals -5. And there's the parabola. Had these been collinear points, that would have dropped out and we'd have found the line that contains all 3 of them. Something slightly more general happens. 2 points, two different points in a plane determine a line. 3 non-collinear points determine a parabola. If we looked at more points, if I had 4 non-parabolic points, they'd determine a cubic. We'd pick up another power of x. So there's a pattern to this that can be generalized. And if they gave us the cubic that passed through 4 non-parabolic, non-linear points, we could find the coefficients of it in the same technique. So it all comes down to this linear stuff and the systems of equation stuff. So that was a bunch, but that takes care of section 1.4. The idea of elementary matrices, we haven't seen the last of. They'll pop up in the next section, conceptually at least. Computationally, we won't use them a great deal. But elementary matrices are important. And in the next section, we'll look at inverse matrices, and that technique will involve row reduction. So if you don't like row reduction, get out of my virtual class, because there's so much of this stuff is just row reduction. From here on out, row reduction. We'll encounter a bunch of new stuff. What you do with the new stuff is you make a matrix and row reduce it. You don't got a clue what to do, make a matrix and row reduce it, because that's probably what you need to do. But you need to practice the row reduction and putting matrices in row echelon form, and preferably reduced row echelon form, because that's a bunch of what follows in this course. I'll see you in section 1.5 on inverse matrices. Bye-bye.